Thank you.
Good luck.
Thanks. Thank you, everyone. Good morning. Welcome. Today, I want to talk about a subject that has bothered software architects for a long time, which is how do we build systems that we can easily change over time? How do we build architectures that allow us to change them without the fear that that change is going to ripple out to some unknown place and break something else? This is something that me and my two co-authors have been thinking about for a while and wrote a book about this that was published a little while ago. And that's exactly what this talk is about, is how do you build architectures that age gracefully and allow you to change them over time? So you have a problem of some kind and you decided you want to use software to solve that problem. So that means you have requirements somehow. We don't really care how you got these requirements. Most of the things that we're talking about are independent of development process. But this is not the only thing you have to think about as an architect. You also have to think about all these other things. Things like performance, scalability, auditability. If you're building a medical record system, for example, you have to be careful about security and privacy and all these other concerns. And in fact, this is really the craft of software architecture. It's given some requirements, given all these other things that we have to think about, what is the best design that creates the least worst combination of those things? As architects, we never get to create the best of anything. What we shoot for is the least worst, because you can never maximize all these things. For example, if I want to improve security, that's almost certainly going to degrade performance. And so my best shot is least worst trade-offs rather than the best design. But this is really the tricky thing about software architectures, balancing all these competing concerns. The other thing that's really tricky here is that there are a lot of these things we can support in architecture. Here's a partial list from Wikipedia of the things you can support in software architecture. These are sometimes known as the illities of software architecture because they almost all end in the suffix illity. But this is always an incomplete list. My colleague Rebecca, who's one of my co-authors, talks about a project that she worked on many years ago where the mandate from the client was we want a centralized architecture. But every design they showed them, the first question the client asked them was, but what happens if we lose Scotland? Because it turns out years ago a free communication outage had caused them to lose communication with their Scottish stores, and this became a really important thing to this organization. And so they started building a set of architectural characteristics that they referred to as Scotlandility. It's this combination of availability and reliability and all those things that keeps them from losing Scotland. And so companies will always build new versions of these things. And in fact, the other problem is none of these things are physics terms. So companies build their own definitions of these things as well. What we're trying to do is add yet another item to this list of abilities, which is this idea of evolvability. But what does that really mean to have an evolvable architecture? Well, let's say that you've chosen performance as a really important characteristic in your architecture. Having an evolvable architecture means that as your system changes over time, performance doesn't change, particularly in a negative way. And so, in many ways, evolvability is sort of a meta characteristic of architecture, because once you've identified the important architectural characteristics, what we're talking about are mechanisms that allow you to protect and preserve those architectural characteristics over time so that you can change your system without fearing that you've broken those important characteristics that led you to this architecture to begin with. But I just said the word change. Change is an interesting thing for us, because we normally think of change as just one thing. But for us, it's actually two closely related things. There's technology-driven change, and there's business-driven change. Business-driven change is the kind of change that you're used to writing software for. So you have one set of requirements and you change them because the market changes, or you're changing the way you do business, or maybe you merge with another company, and you have to take on all their IT and their business and workflows, etc. And in fact, most of the books of the last few years about agile software development have focused on exactly this kind of change, this business-driven change. And we're slowly getting better and better at this. We're building engineering practices that support this over time. But the kind of change we've been less good at dealing with is this technology-driven change, the kind of change that happens to us whether we want it to or not. And that's really the subject of our book and this talk, is this technology-driven change. So think for a moment about the software development ecosystem. That's the combination of all the tools and frameworks and best practices and approaches, all the things we know up until 10 minutes ago about how to write software. That is the software development ecosystem, and this is the place where we live and work on a daily basis. We describe this in the Evolutionary Architectures book as a dynamic equilibrium. It's an equilibrium because it all fits together and it all makes sense, but it's also extremely dynamic and can change and shift at any time without notifying you. And a great example of how dynamic our ecosystem is when Docker hit our ecosystem a few years ago. Once Docker hit our ecosystem, it fundamentally changed our ecosystem just a little bit forever. Even if you're not using Docker yet, it changes the kinds of decisions you can now make against this ecosystem. And so it has an effect on the options available to you and the ways that you think about things and the decisions you make. This is a real problem for us because it doesn't take a very astute observer to realize that in our world, everything changes all the time. In fact, is the pace of change slowing down? Or is it continuing to speed up? And all you have to do is dip your toe into the JavaScript ocean to see that it's definitely not slowing down. But this is a real problem for some roles in architecture, because some architects, like enterprise architects, are expected to be able to tell us 5 years from now what kind of technology assets we should have. But how is long-term planning possible when everything constantly changes in unpredictable ways? Over the last year or so, I've gone to many of the ThoughtWorks offices all around the world, and I've met with a lot of our clients and a lot of the enterprise architects for our clients. And I've been asking them all the same question, and none of them have had a good answer for me. So maybe today, finally, somebody in this room has a good answer for my question, which is, can you tell me with great certainty exactly what JavaScript frameworks you'll be using 2 years from now? And of course you can't, because they probably haven't been written yet. It's impossible to predict the future when the future can constantly change and shift in unpredictable ways. And that's really what we were trying to address in this book. But there was a side effect of the things that we figured out as well, because it turns out that protecting these architectural characteristics over time heavily overlaps with this idea of architectural governance. So we wanted to illustrate a lot of our concepts in the book. All three of us are consultants who worked at ThoughtWorks when this book was written, and we wanted to illustrate concepts derived from our actual client experience, but you can't really talk about client work directly, and so we created a fake company for the purposes of our book called Penultimate Widgets. And it's sort of an English language joke. A lot of people think that the word penultimate means awesome because it has the word ultimate in it. It actually means next to last. So I know someone who worked for a company called Penultimate Consulting, and they thought it meant ultimate consulting company, but it actually meant next to last consulting company. And so that's our fake company. But this is something that actually happened to me. I met with one of our clients. They were in the process of replatforming their system, and they had already come up with a bunch of goals for architectural characteristics like reliability, 4 nines of reliability, et cetera. And there were 66 of them. And I remember that so well because they showed it to me in a spreadsheet that had 66 rows on it. And I said, hey, it's really great that you've identified the goals for your next version of your architecture, but if I roll up in 6 months, how many of these things are still going to be true? And more importantly, how easily can you tell me how many of these things are still true? As I said, it turns out that a lot of the techniques that we designed for preserving architectural characteristics over time heavily overlap this idea of architectural governance, and in particular, automating architectural governance. And I'll show you some examples of this in just a second. So let's talk about some definitions here. We thought long and hard about the definition, both the term and the definition. We thought maybe about continuous architecture, and there's certainly an aspect of continualness here that an evolutionary architecture allows you to make constant change to it, but that doesn't capture the entire thing. We also thought about incremental architecture, and you'll see that this is incomplete too, but in fact made it into our definition. We thought about agile architecture, but that's such a worn out term. And in fact, the things that we talk about don't require agile engineering practices. It makes a few things easier, but that's not a strict requirement. Probably the closest thing we talked about was an adaptable architecture. But Rebecca makes a really good distinction between an adaptable versus an evolutionary architecture. An adaptable architecture is one, so when I say adaptable to most architects, what they imagine is the configuration dialog in Eclipse or IntelliJ or Visual Studio, something with a million switches and configuration settings so that you can adapt it to all sorts of circumstances, or a system where you preserve all existing functionality and keep adapting it toward the future. That's actually a bit of an anti-pattern in software because you can never test all those possible paths, and it just grows and grows and grows in complexity. And so that captures actually the opposite of what we were after. An evolutionary architecture supports fundamental change over time. We're not trying to adapt to every new thing while preserving backwards compatibility. We're talking about fundamentally changing the bits in your software, changing the web framework, changing fundamental parts of your architecture, and evolutionary definitely captures that concept a lot better. So here's our definition. An evolutionary architecture supports guided incremental change across multiple dimensions. And I'll talk about each of these three things in turn, but focus heavily on the guided piece of this, which is the first and most important part of this definition. So let's talk about the guided part of this definition for a second. And let's talk for a second about genetic algorithms. Rebecca is the ThoughtWorks CTO, but she has a past as a computer science PhD and spent some time in the evolutionary computing space. When you're designing genetic algorithms, you're designing algorithms that will go through an iteration, produce a result, and then mutate themselves in well-known ways and produce another result. Now, if you're trying to design a genetic algorithm that produces some sort of beneficial outcome, every time it produces a result, you need to give it some guidance to tell it, are you getting closer to what I think a good solution would be or further away from that? And that mechanism that is used in the evolutionary computing world to do that is called a fitness function. So in evolutionary computing, a fitness function is a type of objective function used to summarize how close a solution is to getting to its set aims. So for example, if I were trying to solve this well-known problem in the machine learning world, the traveling salesman problem, where I have a salesman and he's to travel to a variety of cities, what's the shortest route between those cities? If I were designing a genetic algorithm to try to determine the optimum route, then every time it produced a result, I would try to tell it, are you getting better or further away? And so my fitness function, in this case, would be length of route, because that's the thing I'm trying to optimize for as for results of this genetic algorithm. So we've, in the evolutionary architecture book, borrowed this concept of a fitness function to create what we call an architectural fitness function. This is any mechanism that provides an objective integrity assessment of some architecture characteristic or some combination of architectural characteristics. This is the answer to the question that my clients pose to me. Rather than defining all these architectural characteristics in a spreadsheet somewhere, instead define them as fitness functions. And now I have not only the definition of what those architectural characteristics are, but also a way of verifying that those definitions are still true. And I'll show you a bunch of examples of these things in just a second, but I want to finish out my definition first. The second part of my definition talks about incremental change. And there are two aspects of incremental change that are interesting for us. One is the operational side of incremental change. How do you make small changes at the architectural level without breaking things or causing unexpected side effects? And I'll talk about this in both the abstract and show you a tool that makes that possible at the very end of my talk. The second aspect of incremental change is once you've defined these fitness functions, how do you make sure they're applied on a regular and consistent basis? And that's the realm of continuous integration and deployment pipelines and other mechanisms like that in the agile engineering space. So that's what we mean when we talk about incremental change. And the last part of our definition talks about multiple dimensions. And this is really just the pragmatic awareness that when you talk about evolving real software systems, you can't just talk about evolving the structural aspects of the architecture. And so you see very common things here like performance and scalability and legality here under consideration. But we also include security on this list, which some people might not consider part of architecture, but if it changes the design and the way you construct your architecture, then it's something you need to pay attention to, particularly if you're going to try to evolve your system over time and want to make sure that security is preserved. We also include relational databases here, because you can't evolve a software architecture if you can't evolve your database schema as well. So we have a chapter in our book on evolutionary database design, but that's really just a placeholder for the phenomenally good book, Refactoring Databases by Scott Handler and Pramod Sadlage, which came out 10 years ago. It just had its 10-year birthday, but is every bit as relevant, maybe more so now than when it came out, because you need to be able to restructure data and schemas if you're going to evolve systems over time. And so we have a very holistic view of software systems, not just the structure of architecture, but all the constituent parts and how to evolve those things. And so that's our definition, which now gives me enough to talk about the agenda for the rest of this talk. The first part of which is the definition of evolutionary architecture, which you've just lived through. Now I want to show you a bunch of examples of this idea of fitness functions as a mechanism for protecting and preserving architectural characteristics, but also as a way of automating architectural governance. And then I'll show you some examples of what we mean by incremental change. So here's our definition again of an architectural fitness function. Don't mistake and think that this is some brand new framework that you can download and just apply to your project. In fact, it's any mechanism that you can use to look at and assess some sort of architectural characteristic. And so this bundles up a lot of existing tools that we used to think were different things. And so one of the things that we've done is identified that no, these are really a family of related things together because they're all concerning things about architecture. So before I give you some categorization, things like that, let me show you a concrete example of one of these things that I'm talking about. So let's say that you're building a component-based system of some kind. As an architect, one of the things you want to try to prevent in that component-based system are cyclic dependencies between your components. That's where one component talks to another component, talks to another component, and talks back to the original component. This is an anti-pattern because now it's difficult to reuse one of those components. I have to take the whole rat's nest with me, and of course if these are also connected to a bunch of other components, this makes my architecture less and less structured and more like a big ball of mud. The problem though is, if you're using a language like Java or .NET, and you're a developer and you're typing along in your IDE, and it pops up, you use reference some class you've never referenced before, what does your IDE do for you? Pops up a dialog that says, do you want me to auto-import that class for you? And you swat that dialog away so fast now you don't even see it anymore. It's like a sneeze reflex now. As soon as that dialog comes up, it's wham, and just right back to typing. If I came over 5 minutes later and said, did you just auto-import something? No, I haven't auto-imported anything all morning, I swear. But what you're doing is tangling up all of your relationships like this. As an architect, how can you prevent this from happening? You have to stand over every developer's shoulder and watch them type and go, no, don't auto-import that because you're going to mess things up. Instead, what you do is write a fitness function for it. This is actually using a quite old tool in the Java world called JDepend, which understands the structure of Java code. And so you can write this fitness function and put it into your build. And now trigger-happy developers who are trying to tangle up all of your components cannot do that anymore because now you can put a check in place to make sure that doesn't happen. This is an example of a very low-level code metric-based fitness function. So as I mentioned, this will actually encompass a lot of different mechanisms. Things like metrics, which I just showed you an example of. I'll show you another example in a second. There's specialized unit testing libraries that I'll show you some examples from. Things like monitors, new things like chaos engineering fall under this category of fitness functions for us. And there will in fact be new mechanisms people build, but there are lots and lots of mechanisms we can use now to preserve architectural characteristics. So one of the things we did in the book was build a bunch of categories and build a nomenclature around this idea of fitness functions. Some of these have to do with the scope of the fitness function. So an atomic fitness function looks at a single characteristic in architecture. The one I just showed you is atomic because all it cares about is how components are coupled together. Holistic ones look at a combination of factors. As I mentioned before, very often performance and security will interact with each other in interesting ways, and you might want to test those together to see how that interaction is working. That's an example of a holistic fitness function. We also talk about the invocation mechanism. Triggered is triggered like a unit test. A continuous is something that runs like a monitor all the time in some sort of system, either a staging environment or something like a production environment. We prefer most of these to be automated as much as possible, but it's okay if some of these are manual, and in fact, some of them are a combination of automated pieces and manual pieces. I'll show you an example of one of those in just a second as well. One of the most important parts of our definition of a fitness function is that it must be objective. But the outcome can be either static or dynamic. So static is easy to understand. That's like a binary pass-fail of a unit test, red or green, or number value. But it can also be dynamic. So for example, very often when we're doing scalability tests, scalability is a combination of performance and number of concurrent users. And very often, as number of concurrent users go up, it's okay for performance to start going down, but you don't want it to fall off a cliff. And so you can put acceptable ranges of values for performance as scale goes up. That's a dynamic fitness function. So now you're basing the performance value on some extra context, like number of concurrent users. But it's still an objective outcome. I can still define objectively a range and determine did I make it in that range or not. We also have temporal fitness functions, which are time-based. For example, let's say that I'm supposed to update a security library every 2 weeks, and after 3 weeks that hasn't happened, I can raise an alarm. Or let's say that I want to set up a fitness function that says, warn me if my performance continues to degrade over a 3-month time. So it's gradually getting worse and worse and worse. You can set up a fitness function to look for those kind of anti-patterns in your architecture as well, because that's one of those creeping things that you don't realize until it becomes critical. And if you start tracking that, it's easier to see what's going on there. One of the questions we sometimes get is, are there domain-specific fitness functions? And this is a good place to talk about the real distinction here between what we call fitness functions and the traditional kinds of testing mechanisms used in agile projects. So we have things like unit tests, functional tests, and user acceptance tests, and I'm going to show you examples of fitness functions using unit testing libraries. So what's the real difference here? Well, the difference is fitness functions should look purely at architectural characteristics. So I should be able to describe those things purely in the abstract. For example, when I talk about elasticity of users, what I'm talking about is an architecture that will allow bursty groups of requests, a whole bunch of people at one time showing up at a website. When I describe that problem, it doesn't matter if the website is an insurance application or streaming video application or catalog site or gaming site. So I can talk about elasticity purely in the abstract, and that means it's an architectural characteristic and therefore subject to a fitness function. If I need to know anything about the problem domain to be able to write the test, then it's a traditional unit, functional, or user acceptance test. So let's say that I had a requirement in my system that says that I was an auction system and every user has to be graded by a reputation index. Well, the first question I would have is, well, I have to go to a business analyst and find out what this reputation index means. That I have to go to the business analyst means it's part of the design of the application, not necessarily an architectural characteristic. Now, everything in architecture is a trade-off. There are no binaries anywhere, so this is a spectrum as well. But very often these things lean heavily to one side of purely abstract architectural characteristics versus something you would actually design your application specifically around. So let me show you some examples of these fitness functions, enough of this categorization and that kind of stuff. So let's look at some examples. And here's another example, also at the very low level code level. Directionality of imports. Let's say that you have packages or namespaces for persistence, web, and util, and it's perfectly okay for persistence and web to import util, but you never want some trigger-happy developer to accidentally import all of web into util. How do you prevent that? This is, again, using JDepend, a fitness function. because it understands how packages wire together, you can tell it how you want things wired together in your ecosystem, and this will verify that they're wired together correctly every time you run this test. There's a similar tool in the .NET space called Independ that will also allow you to write these same sorts of tests. So these are both examples of very low-level code metric-based fitness functions. Let's look at, and these are what are called atomic because they just look at one characteristic, and triggered because they run as unit tests. Let's look at another example of a triggered atomic fitness function, but this time at a much higher level of architecture, at the integration architecture level. This is a common problem in really dynamic environments like microservices. So the scenario is you have the service provider team in red on the left, and they're providing some overlapping bits of information to all three teams on the right. The question now becomes, if these are all independent, autonomous teams, how can we make sure that we preserve the integrity of those integration points so that they don't change in a way that breaks how they're integrated with one another? The common practice in the microservices world is to use this idea of consumer-driven contracts, where each of the teams on the left or the right, the consumers, put together a set of tests, hand it to the team on the left, the provider, and that team promises, I will keep those tests green always for you. So that if the team in red does in fact change and doesn't break anything, then they change in a way that nobody cares about. If that change does break something, then that becomes a placeholder for conversation. Let's get these teams back together again and reestablish this contract. And so as an architect, my concern here is I don't want these independent teams evolving in such a way that breaks my integration architecture. Consumer-driven contracts allow you to make sure that those contracts are preserved without these teams constantly having to be in touch with one another. So let's talk about how this idea overlaps with this idea of automating architectural governance. And one of our goals in the evolutionary architecture world is to get architects to stop using vague, meaningless terms like this. We have allowed architects too long to be too vague about the things that they are talking about. Because your architect comes down out of the ivory tower and goes to the developers and says, we want a maintainable code base. And then they drop the whiteboard marker and walk out of the room. And everybody goes, what does that even mean? There's nothing objective here. There's nothing testable. There's nothing we can build a fitness function around. And so what I'm asking you as architects is drill one level deeper into this and go, well, what are objective criteria in my code base that leads me to a more maintainable code base? Drill one level deeper. Well, cyclomatic complexity, controlling the complexity of my functions or methods, makes my code base more maintainable because very complex code is hard to maintain, and less complex code is easier to maintain. And so if I put a threshold on cyclomatic complexity across my project, I can start beating down some of that complexity. Consistent naming conventions throughout projects makes for more maintainable code. Things like controlling, coupling. There are lots of metrics tools that allow you to look at incoming and outgoing, afferent and efferent coupling. Postel's law, immutability. There are lots of definitive ways, objective ways you can test your code that drives you toward a more maintainable code base. So let's take something, for example, like cyclomatic complexity. How can that be used to wire up something like a fitness function? So this is an example, and this supports what I said earlier, that many of the metrics and techniques that we talk about have actually been around for quite a long time. We only recently started calling these things fitness functions. And this is a good example. This happened for me more than a decade ago. I was working for an insurance company in the US, and the architects there were quite concerned because they had a lot of very junior developers, and they were worried about the code quality those junior developers were going to be producing. And in fact, this one junior developer was tasked with writing something on the back end in Java and something JavaScript on the front end. And this being not a very good developer, their task was to write something that concerned all 50 states. And so they ended up writing some code that essentially said if state equals Georgia, then do something for Georgia, else if state equals Alabama for all 50 states, and creating this big, giant, long method. But the architects on this project had set up a check in continuous integration for cyclomatic complexity. And it said no method with a cyclomatic complexity over 50 shall be allowed in this code base. And I can tell you exactly how they picked that number 50. There used to be a Java metrics tool called crap4j, and it was a combination of code coverage and cyclomatic complexity to determine how crappy your Java code was. And if your code, cyclomatic complexity, ever got up to 50 or above, no amount of code coverage would make your code not crappy. And so that's the threshold they set, which is still a monstrously high threshold. It really should be like 2 or 3. But 50 is the number they said, and when this developer tried to check into this code base, it got rejected because it failed what we would now call a fitness function. My friend Glenn Vandenberg has a great quote that bad developers will move heaven and earth to do the wrong thing. That the amount of ingenuity that terrible developers will put into creating train wrecks, if they'd put half that ingenuity into actually solving problems, the world would be a better place, but that doesn't happen for whatever reason. And so this being kind of a bad developer thought, how can I solve this problem that it's yelling at me about? Oh, I know how to solve that problem. I'll just write that code in JavaScript instead. So that's exactly what they did. They wrote basically this same method in JavaScript on the front end, but the architects outsmarted them because they had a cyclomatic complexity check on the JavaScript code too. And so when he tried to check this in, it rejected it as well. And so this developer went to the architect in great frustration and said, look, the stupid code base won't let me check anything in. And that's the day they learned about the strategy design pattern. And that you shouldn't create big, huge, ugly methods like this. Now, we're not trying to use this fitness function mechanism as a way for architects to create these kind of police states. But I've got a question for all you architects in the room. What's the most complex code in your code base right now? You don't know, do you? But you'd like to know, wouldn't you? And you'd like some mechanism to be able to put at least some guardrails or governors around really, really bad code. And a lot of these things can be checked with things like metrics. These are all very low-level code-centric kind of tools that are done at build and compile time and something like continuous integration. But we had an entire category of these fitness functions that we call continuous, which are based on things that, like monitors and things that run in staging or production-like environments. And one of the best examples of a continuous fitness function that's already used out in the world quite heavily is Netflix's Chaos Monkey and the entire eventual simian army that they open sourced. When Netflix moved to AWS as their operations center, they worried, and so created this simian army and Chaos Monkey to torture their architecture to see how it would react to all these different things. And in fact, 2 of the members of the simian army are particularly interesting to us. One is the conformity monkey, and the other is his close relative, the security monkey. So the conformity monkey is the way Netflix architects impose architectural governance within their ecosystem. So for example, let's say that they decide from a governance standpoint that we want to make sure that every one of our services responds usefully to all the RESTful verb requests. So the conformity monkey would go check each service, ask it all the RESTful verbs, and if one of them didn't provide a useful response, it would kick it out of production. So as a developer at Netflix, you didn't have the option to skip configuring one of the RESTful endpoints, because if you did and tried to put it live, the monkey would just kick it back to you and you'd have to fix it. The security monkey is an even better example of this, because it looks at all the services to make sure that it doesn't have security vulnerabilities or open debugging ports and other bad things like that. But every developer knows that you're not supposed to release unsecure containers for your code. But where is that on the developer's priority list as they're trying to get this feature complete and they're trying to get this environment configured and they're trying to get this thing debugged and there's schedule pressure, there's this other thing I've got to do and then there's this other thing I've got to do? I mean, it might be in the top 20, maybe top 30, but it gets skipped and it's easy to skip. So there was a book that came out a few years ago called A Checklist Manifesto. And it talks about professions like airline pilots and surgeons who heavily use checklists. And it's not because they're forgetful or they don't know their job. It's because in highly technical jobs, it's very easy to accidentally skip important steps. And they use checklists to make sure they don't do this. That's what this is checklists for developers. Did you remember to do this? Did you remember to turn the debugging ports off? Did you remember to not write awful code? Did you remember these things? So this is a way that architects can gently provide checklists that are executable barriers for bad code entering into your code base. So there are lots of really nice tools that have been invented around this space, around fitness functions, and one of them is a tool called ArcUnit. So one of the common annoyances you may have as an architect are lazy developers who throw generic exceptions, and then you catch it and you don't know why it was thrown because it's generic. Look at the next to last test here. No classes should throw generic exceptions. This is a pre-configured governance rule in ArcUnit, and once you snap that into place in your code base, no developers are allowed to throw generic exceptions anymore. They must subclass it and throw a proper subclass exception. The last one here, what happens, how do you prevent, if you've decided as an organization to use a third-party logging package, how do you prevent developers from accidentally using the one that's built into the platform? This is the way you prevent developers from accidentally using the one built into the platform. You build a governance rule that prevents them from doing that. Remember I talked about naming conventions earlier? Interfaces should not have class names ending with the word interface. Interfaces should not have simple class names ending with the word interface. Look at the bottom one. Interfaces must not be placed in implementation packages. This is another policy that you may want to institute as an architect, and by building this as a fitness function, you make sure that this policy is adhered to. But here's an even better example. Let's say that you as an architect designed a layered architecture with a distinct presentation layer, business layer, and data layer. And you hand this over to developers to implement this for you. But some developers are always itching to break some of these rules. For example, the reporting team will say, well, you know, it's taking too long to get through all those layers, and performance reasons, we need to go directly from the presentation layer right to the database. But as an architect, if you allow that to happen, you're chipping away at the reason you built those layers of separation to begin with, because now database schema changes are fossilized at the top and bottom of your architecture, and all the layers, the purpose of the layers have gone away. But how do you make sure that developers don't cheat on designs like this? This is how you prevent that from happening. Look at the first test here. This is using the Hamcrest matchers from the JUnit world, so you can write these very fluent interface assertions. No classes that reside in a package service should access classes that reside in a package controller. Now, many of you as architects have written almost this exact same English or Hungarian sentence somewhere in a wiki or some terrible SharePoint portal, and it was right once, read never by another human being. You wrote it down because it's an important principle that you're trying to establish, but it has no teeth. There's nothing that forces developers to think about this stuff. And where is this on the developer priority list? Is this in the top 50? Top 60? By wiring it into your build, you make sure that people can't ignore important things within your ecosystem. Here's an example of a custom governance rule that you can build in ArcUnit as well. This one says, well, I need to use this third-party class, but it has security concerns, so I always need to call it through this third-party wrapper. This says never instantiate one of those things directly and always access it through this third-party wrapper. So you can control things like instantiation. Is this thing allowed to talk to this thing? Layer isolation, and all sorts of interesting structural aspects of your code through something like ArcUnit. And the inevitable question people ask me is, well, that's really slick, but it's only in the Java world. In December this last year, inspired by ArcUnit, we got NetArcTest, which is the equivalent in the .NET ecosystem. Uses the exact same kind of fluent interfaces, so here's controllers should not directly reference repositories, just like we saw that kind of layer test in ArcUnit. Here's one that says only classes in the data namespace can have a dependency on system.data. Here are a bunch of things about positions of things. Things like all service classes should be sealed so that you can't subclass from them. These are all kinds of things that you can test using this family of tools in the, that's gradually showing up more and more in our world. But sometimes you just have to wire up your own solutions to these problems. So here's an example. I used to work for a while for a financial services company outside of Manhattan, and they used a variety of open source libraries and frameworks. And at one point, one of the lawyers got worried about viral license terms in the open source tools we were using. He didn't want us to accidentally take on some open source tool that would force us to use the same license on our code. And so we chased down the license files for all these tools and let the lawyers look at them. And then one of the lawyers asked a really awkward question. What happens if one of these libraries changes the terms of their license during a software update? Being a good lawyer, he had in his back pocket a case where that had happened. The Qt user interface library years ago fundamentally changed their license during a minor software update, so now this is something we have to pay attention to. So here's the system we built to do that. We knew the location of that license file in each one of those libraries and frameworks, and so we took the entire license file, hashed it, and put that value into a database. Then every time one of these things updated itself, we went and grabbed its license file, hashed it, compared it against the value in the database, and if it didn't match, we called the lawyer. Hey, would you look at this, anoint this one as okay, this will become the official version in the hash database. And so basically what we built was a mechanism that triggered us anytime one of these things changed so we could react to it and do useful things with it. So this is a combination of an automated and a manual process, but this served exactly the purpose that we needed. Now there's software that does this for you now. Black Duck software and several other software packages monitor this stuff for you now. So there are lots of tools in this space to help you do this kind of stuff. So let's talk about putting this into practice. From a mechanical standpoint, the first thing you do is identify dimensions in your architecture. And this is not every single thing in your architecture, but this is really now becomes a prioritization exercise, because what really is critically important in your architecture that you want to preserve over time, this now gives you a concrete way to look at how much it costs to implement things like performance, because performance costs what it takes me to implement and maintain the performance fitness function. I can assess how much effort that takes, and now I have a concrete cost of how much performance or scalability or elasticity or all these architectural characteristics cost. This also changes a disastrous fix-it emergency cost into a constant fixed maintenance cost of just keeping these fitness functions maintained, because if you do this, you'll never be surprised by performance anomalies because you've been checking it every time you make a change to your code base. Once you've identified the important dimensions in your architecture, you define fitness functions for them. These are the protections over time that preserve those characteristics. And then once you've built those, you use deployment pipelines and or continuous fitness functions to make sure these get applied on a regular basis. This is part of our idea of incremental change, is using tools like CI, deployment pipelines, to make sure that those things get applied on a regular basis. Many of these will come at project inception, but these are meant to be living, continual parts of your code base. So you will continue to refine these things over time, just like you keep up with unit tests and functional tests and user acceptance tests. These really do define your architecture in many ways in an executable form, and so you keep those up to date, just like other things in your architecture. And one last example here around incremental change that I mentioned before. I mentioned deployment pipelines. Let's talk about the operational side of incremental change for just a second. And I'll talk about this in the abstract and then show you a tool. So let's say that we have a Penultimate Widgets website, and it has several different services, and one of them is a star rating service that allows people to star rate how much they like widgets or sales reps, et cetera. And one day we release a better version of star ratings that allows half-star ratings. And we put it live. We don't force anyone to start using it yet, but this is now just a new capability that exists in our architecture. And over time, more and more of these services that need star ratings will migrate over to this improved star rating service until eventually no one's pointing to the old one anymore. One of the magic tricks Netflix taught us about architectures like this is you monitor not only the services, but also the routes between services. And any service that no one's routing to anymore automatically gets disintegrated out of the ecosystem. In fact, this is such a common thing at Netflix that they have a monkey that manages this. This is the janitor monkey's job, cleaning up services that no one loves anymore in their architecture so they don't take up resources anymore. But here's an actual tool that allows you to do this. So this is from the GitHub engineering blog, an entry called Move Fast and Fix Things. GitHub is a very agile engineering organization. They do continuous deployment. They average 60 deploys a day. And this describes a problem they had with merge. It turns out since day one at GitHub, the way they have merged two files is to shell out to a shell script, tell command line Git to merge them, and then suck it back into GitHub. And that works great because command line Git knows exactly how to merge things, but it doesn't scale particularly well. And so this is about them biting the bullet and rewriting their own in-memory merge, which they did. They did their due diligence testing on it, but now here comes the scary part. Now they have to put it live. But how do you put this live without breaking stuff? Because merge has never had a bug logged against it. The way they did this and open sourced it on your behalf is create this tool called Scientist. And they've already ported this to about a dozen other languages. What Scientist allows you to do is conduct experiments at the architectural level. So Scientist creates experiments blocks with a use and a try. Use is the old code we're trying to replace, and try is the brand new code we're trying out. So every time it hits this experiment, it always executes use and returns that to the user, but then it also, with a percentage, it executes try, and that was for 1% of the cases. When it executes try, it randomizes the order, swallows and records exceptions, and publishes all this stuff to a dashboard. So here's when they first went live. You can see along the bottom some tiny red tick marks, so I'll zoom in on the bottom. Here are the places that try and use disagreed. This hasn't affected their users yet because this has all been happening in the background. Users always get what came from use, but here are bugs that they can go find. Here's the performance graph, and the green line is the better performance for the new solution, which is what they wanted. They ran this experiment for 4 days until they had 24 hours with no mismatches or slow cases. Over the course of those 4 days, they did more than 10 million comparisons between old and new, so they had really high confidence when they left that new code in place that it was doing exactly what they wanted. That's a great example of incremental change at the architectural level, the ability to surgically change something without breaking the things around it, and exactly what we're talking about with incremental change. I'm out of time. I encourage you to go to the evolutionaryarchitecture.com website, which has a bunch of resources and a bunch of other goodies on it. And of course, you can use our book as well. Thank you very much for coming. I hope you enjoyed it. I hope you learned some stuff about architecture. Thank you. Thank you.
Thank you so much, Neal. That was super awesome. We have some time for some questions.
Sure, absolutely.
So the first one is super hyped. This requires heavy upfront investment. By the time some projects get the resources, they are already valuable. So how would you begin?
Well, there's nothing that says you have to do this up front. So even if it's an existing project, you can say, well, what are the most important things here? Performance, scalability, and elasticity. Well, let's build fitness functions around those. You don't have to build every single thing. You start with the most important things, and then it becomes a question of how much effort is this work versus how important is this next thing. And at some point, you'll get to the point where, well, it's not that valuable to spend the effort to write that, and now you've found exactly the set of fitness functions that are most important to your project.
All right, thank you. Next question. Can check-style sonar build tools used instead of these fitness functions? They can solve most of the problems. What other benefits does fitness functions give?
You're making the mistake of thinking fitness functions is some alternate thing you download. Sonar is a fitness function. They just don't call it that, but that's exactly what it is. It's any mechanism that allows you to verify any architectural characteristic. Sonar, every metrics tool can be used for this. Not every metric that Sonar provides is useful as a fitness function, but many of them are because they address architectural characteristics. So there's not a unique one tool. It's a combination of tools, and Sonar is a good example of one of those.
All right. If your developers don't know the strategy design pattern, is this really the best way to discover and fix that problem? Shouldn't architects focus a lot more on training than the governance?
Well, of course, this is not the education mechanism that I recommend for your developers, slapping them when they do something horribly wrong. Hopefully, you've got developers who won't do horribly wrong things to begin with, or you're pairing with junior developers to keep them from doing that, because that's a much better feedback loop rather than letting them do a horrible thing and then later telling them it was a horrible thing. If you keep them from doing the horrible thing in the first place by pairing, then the horrible thing never exists on Earth. And then that's a better Earth to live on.
Yeah. Cool. Let's do one more. Is there any tool or framework that can already be integrated in these build pipelines to inculate fitness functions?
Absolutely. ArcUnit, NetArcTest, JUnit, Sonar, every metrics tool on Earth that can be wired into continuous integration can be used as a, again, you're making a mistake of thinking this is some unique library that you have to download to do something with. This is a category. This is a nomenclature that ties together a whole bunch of related tools, including chaos engineering and all these metrics tools. Those are all ways to implement fitness functions. So it's really just a term that describes a whole set of mechanics and techniques.
Amazing. Huge hand. Let's go. Thank you so much.
Thank you.
And this is a tiny gift from Craft. There is
Yeah, perfect. That's great.
Thank you so much.
Thank you. Thanks a lot.
Thanks.